Picture yourself standing on the shores of an ancient sea 50 million years ago. The air is warm and humid, filled with the calls of unfamiliar birds and the gentle lapping of waves against a coastline that no longer exists. The world you're imagining is Earth during the Eocene epoch, a time when our planet was dramatically different from today. There were no ice caps at the poles, no grasslands stretching across continents, and certainly no whales gliding through the depths of the oceans. Instead, if you were to scan the waters of that ancient world, you might spot something extraordinary. Along the muddy banks of rivers and shallow seas, strange four-legged creatures wade through the water, their wolf-like bodies moving with surprising grace as they hunt for fish. These animals, covered in coarse fur and equipped with sharp teeth, represent one of evolution's most remarkable experiments. They are the ancestors of the largest animals ever to live on Earth, beginning a journey that would transform them from land-dwelling hunters into the magnificent whales we know today. This is the story of when whales returned to the sea. It's a tale that spans millions of years, revealing how life adapts, transforms, and finds new ways to thrive in the face of changing environments. Tonight, as we explore this incredible evolutionary journey, we'll discover how creatures no bigger than wolves became giants of the deep, how legs became flippers, and how the call of the ocean proved irresistible to mammals who had once walked on solid ground. The story begins in a world recovering from catastrophe. Just 15 million years earlier, a massive asteroid had ended the reign of the dinosaurs, leaving behind a planet ripe for new forms of life to emerge and flourish. Among the survivors were small, furry mammals, no larger than shrews, who had lived in the shadows of the great reptiles for over 100 million years. With the dinosaurs gone, these humble creatures found themselves inheriting a world full of empty ecological niches waiting to be filled. In the warm, tropical climate of the Eocene, dense rainforests covered much of the globe. Where today we find the dry landscapes of Egypt and Pakistan, vast river systems carved through lush vegetation, eventually emptying into the Tethys Sea, a great tropical ocean that stretched from what is now the Mediterranean all the way to the Indian subcontinent. It was along the shores of this ancient sea that our story truly begins. Among the many mammals exploring new ways of life during this time were the mesonychids, wolf-like predators with long skulls and powerful jaws lined with sharp teeth. These animals had evolved from the same ancestral group that would eventually give rise to modern hoofed mammals, though they looked nothing like the gentle herbivores we might expect from such lineage. Instead, they were fierce carnivores, perfectly adapted for hunting on land. But evolution rarely follows a straight path, and some descendants of these early mammals began to explore a different way of life. Rather than competing with other predators on land, they discovered that the water's edge offered rich hunting opportunities with fewer competitors. Fish were abundant in the shallow seas and river estuaries, and for a mammal clever enough to wade into the water, an entire world of prey awaited. This brings us to our first character in the whale evolution story, a creature that lived approximately 50 million years ago along the banks of ancient rivers in what is now Pakistan. Scientists have named this animal Pachycetus, meaning whale from Pakistan, though when you first see its fossilized remains, you might wonder why anyone would associate it with whales at all. Pachycetus was roughly the size of a large dog or small wolf, measuring about 6 feet in length from nose to tail. Its body was lean and muscular, built for both walking and swimming, with 4 sturdy legs ending in small hooves. Its skull was elongated, somewhat like a wolf's, but with subtle differences that would prove crucial to understanding its place in evolutionary history. Most importantly, the structure of its inner ear contained features found only in whales, a discovery that would revolutionize our understanding of whale origins. Unlike modern whales, Pachycetus still possessed external ears and nostrils positioned at the tip of its snout, just as we see in most land mammals today. Its teeth were sharp and varied, including incisors for cutting, canines for piercing, and molars for grinding, suggesting a diet that included both meat and possibly some plant material. The wear patterns on these teeth tell us that Pachycetus was catching and eating fish, but it was doing so in freshwater environments, hunting in rivers and streams rather than in the open ocean. The bones of Pachycetus reveal fascinating clues about its lifestyle. The density of its limb bones is much greater than what we see in typical land mammals, but similar to what we find in aquatic animals today. This increased bone density, known as pachyosteosclerosis, serves an important purpose for semi-aquatic animals. It acts as natural ballast, helping them stay submerged while hunting underwater, rather than bobbing to the surface like a cork. Imagine Pachycetus hunting along the muddy bottom of a slow-moving river. Its dense bones allow it to walk along the riverbed while mostly submerged, moving with the deliberate grace of a modern hippopotamus. Its keen eyesight spots movement in the murky water, perhaps a fish swimming too close or a crab scuttling across the bottom. With a quick lunge, its powerful jaws snap shut, capturing prey that land-based predators could never reach. This hunting strategy proved remarkably successful. The fossil record shows us that Pachycetus and its relatives thrived for millions of years, gradually becoming more and more adapted to life in and around water. But Pachycetus was just the beginning of the story. Over the following millions of years, its descendants would undergo one of the most dramatic transformations in the history of life on Earth. As we move forward through time, approximately 3 million years after Pachycetus lived, we encounter another crucial player in our evolutionary tale. In the same region of ancient Pakistan, but in slightly younger rock formations, paleontologists have discovered the remains of a creature that represents the next major step in whale evolution. This animal, known as Ambulocetus natans, whose name literally means walking swimming whale, shows us just how quickly evolution can reshape a lineage when environmental pressures favor change. Ambulocetus was considerably larger than Pachycetus, measuring about 10 feet in length and possessing a body plan that seems almost fantastical to modern eyes. Picture a mammalian crocodile with the posture of a giant otter, and you begin to get a sense of what this remarkable creature looked like. Its limbs had become longer and more paddle-like, though it still retained 4 distinct legs with webbed feet, ending in small hooves, a reminder of its terrestrial heritage. The skeleton of Ambulocetus tells us a story of compromise, an animal caught between 2 worlds and thriving in both. On land, it likely moved with the awkward grace of a modern sea lion, using its powerful limbs to haul its bulky body across beaches and riverbanks. But in the water, Ambulocetus was transformed. Its long, flexible spine allowed it to swim with an undulating motion, much like a modern otter, while its enlarged hind feet served as effective paddles for propulsion. The skull of Ambulocetus had begun to show the changes that would eventually lead to the whale skull we recognize today. The nostrils had started their journey backward from the tip of the snout, though they were still far from the blowhole position we see in modern whales. More importantly, the structure of the inner ear had evolved to function effectively underwater, allowing Ambulocetus to hear and hunt in aquatic environments where sound travels differently than it does in air. Chemical analysis of Ambulocetus' teeth reveals another fascinating detail about its lifestyle. The isotope ratios preserved in the tooth enamel show that this animal spent time in both fresh and salt water, suggesting it was equally at home in rivers and coastal marine environments. This flexibility would prove crucial as the descendants of Ambulocetus began to venture further from shore and deeper into the ancient seas. The hunting behavior of Ambulocetus was likely similar to that of modern crocodiles. It probably lurked in shallow water near shorelines, using its excellent underwater hearing to detect the movements of fish and other prey. When an opportunity presented itself, Ambulocetus could launch itself forward with surprising speed. Its powerful tail and hind limbs, providing the thrust needed to capture unwary victims. But perhaps the most remarkable aspect of Ambulocetus was its adaptability. Fossil evidence suggests these animals could travel considerable distances, both on land and in water, following seasonal migrations of prey or moving between different hunting grounds as environmental conditions changed. This mobility would prove essential as their descendants began to explore the deeper waters of the ancient Tethys Sea. As millions more years passed, the descendants of Ambulocetus continued to evolve, each generation becoming more and more adapted to aquatic life. The fossil record from this period shows us a parade of increasingly whale-like creatures, each representing another step along the path from land to sea. Animals like Rhodhocetus began to show the first hints of the tail fluke that would become so characteristic of modern whales, while still retaining functional hind limbs. During this crucial period in whale evolution, roughly 45 to 35 million years ago, the global climate began to change in ways that would profoundly influence the direction of whale evolution. The warm, tropical conditions that had characterized the early Eocene began to give way to cooler, more variable weather patterns. Ocean currents shifted, creating new patterns of upwelling that brought nutrients from the deep sea to surface waters, leading to explosive growth in marine plankton populations. These changes created new opportunities for large marine predators. The seas were becoming richer in food, but that food was often animals to travel long distributed in patches, requiring distances between feeding areas. For the increasingly aquatic descendants of Ambulocetus, these environmental changes represented both a challenge and an opportunity. Those individuals best adapted for long-distance swimming and deep-water hunting would have significant advantages in this changing world. It was during this period that we begin to see the emergence of the first truly oceanic whales. These animals, known as basilosaurids, represent a quantum leap in whale evolution. Unlike their semi-aquatic ancestors, basilosaurids were fully committed to life in the ocean, with body plans that would have made them clumsy and vulnerable on land, but supremely effective in the water. The most famous of these early ocean whales is Basilosaurus, a serpentine giant that could reach lengths of up to 60 feet, making it one of the largest predators of its time. Despite its enormous size, Basilosaurus retained tiny hind limbs, vestigial remnants of its terrestrial ancestry that were far too small to support the animal's weight on land. These miniature legs serve as powerful evidence of whale evolution, representing one of the most compelling examples of vestigial structures in the fossil record. The body plan of Basilosaurus was revolutionary for its time. Its spine had become incredibly flexible, allowing for the undulating swimming motion that we still see in modern whales. The forelimbs had evolved into true flippers, with elongated finger bones encased in flesh to create broad, paddle-like structures perfectly shaped for steering and maneuvering underwater. Most remarkably, the nostrils had moved significantly backward on the skull, approaching the position of the modern whale blowhole, allowing Basilosaurus to breathe efficiently while spending most of its time submerged. The teeth of Basilosaurus reveal it to have been a formidable predator, capable of taking prey as large as other whales. Fossil evidence shows that Basilosaurus hunted Doruden, a smaller contemporary whale, suggesting that the ocean ecosystems of the late Eocene were complex environments where whales had already begun to occupy multiple ecological niches. But Basilosaurus and its relatives were not the direct ancestors of modern whales. Instead, they represent a successful but ultimately dead-end branch of early whale evolution, giants that ruled the ancient seas for millions of years before eventually disappearing, leaving no descendants in the modern world. The true ancestors of today's whales were smaller, more generalized animals that would prove better suited to surviving the environmental changes that lay ahead. As we follow the thread of whale evolution through these ancient seas, we begin to see the emergence of the two great lineages that would dominate the oceans for the next 30 million years. The first group, the ancestors of modern toothed whales, would eventually develop the sophisticated echolocation systems that allow dolphins, porpoises, and sperm whales to hunt in the darkest depths of the ocean. The second group, the ancestors of baleen whales, would evolve an entirely different strategy, becoming filter feeders capable of processing enormous quantities of small prey. Both groups were still millions of years away from reaching their modern forms, but the fundamental body plan of the whale had been established. These were animals fully committed to ocean life, with streamlined bodies, powerful tail flukes, and respiratory systems adapted for holding their breath during long dives. The transformation from Pachycetus to these early modern whales represents one of evolution's most dramatic makeovers, a complete reinvention of mammalian body architecture. In response to the opportunities offered by marine environments, the story of these early ocean-dwelling whales reveals something profound about the nature of evolutionary change. While we often think of evolution as a gradual, steady process, the transformation of whales tells us that life can sometimes take dramatic leaps when the right conditions align. The warm seas of the Eocene provided a perfect laboratory for experimentation, allowing mammals to explore body plans and lifestyles that would have been impossible in the harsher environments that came before or after. During this golden age of whale evolution, the ancient Tethys Sea teemed with life in ways that are difficult to imagine today. Massive kelp forests swayed in the currents, providing shelter for countless species of fish and invertebrates. Coral reefs, far more extensive than any we see in modern oceans, created complex three-dimensional habitats where predators and prey engaged in an endless dance of survival. Into this rich ecosystem came the early whales, bringing with them the intelligence and adaptability that had served their mammalian ancestors so well on land. The success of these early whales can be measured not just in their size, but in their diversity. Fossil sites from this period reveal a stunning array of whale species, each adapted to different aspects of marine life. Some were shallow water specialists, using their keen eyesight to hunt fish in the clear waters near shore. Others ventured into the deeper parts of the ocean, developing enhanced hearing to locate prey in the perpetual darkness of the abyss. One of the most remarkable aspects of early whale evolution was the speed at which these animals developed sophisticated hunting strategies. Within just a few million years of entering the ocean, whales had evolved complex social behaviors that allowed them to coordinate their hunting efforts. Fossil evidence suggests that some species hunted in groups, working together to corral schools of fish or to bring down larger prey that would have been impossible for a single individual to handle. The sensory world of these early whales was undergoing revolutionary changes as well. Life in the ocean demanded new ways of perceiving the environment, and the descendants of land mammals rose to meet this challenge with remarkable innovations. Their eyes evolved to function effectively in the dim, blue-filtered light that penetrates seawater, developing enhanced sensitivity to the wavelengths that travel farthest through the marine environment. Perhaps even more dramatically, their hearing was transformed to take advantage of the unique properties of sound underwater. In the ocean, sound travels much faster and farther than it does in air, opening up possibilities for long-distance communication and navigation that would have been unimaginable for their terrestrial ancestors. The inner ear structures of early whales show progressive modifications that enhance their ability to process these underwater sounds, laying the groundwork for the sophisticated acoustic abilities of modern cetaceans. As these changes accumulated over millions of years, the descendants of Ambulocetus and its contemporaries began to diverge into distinct lineages, each following its own evolutionary path toward mastery of marine environments. The fossil record from sites across North Africa and the Indian subcontinent provides us with snapshots of this diversification, revealing animals that were becoming increasingly specialized for different aspects of ocean life. Some lineages evolved toward gigantism, developing the massive body sizes that would allow them to pursue large prey or to process enormous volumes of water for filter feeding. Others remained smaller, but developed enhanced agility and speed, becoming the ocean's equivalent of aerial pursuit predators. Still, others explored the middle ground, developing moderate sizes and generalized hunting abilities that would prove remarkably successful across changing environmental conditions. The transformation of whale limbs during this period represents one of evolution's most elegant solutions to the challenge of aquatic locomotion. The forelimbs of early whales underwent a remarkable metamorphosis, with the bones of fingers and arms elongating and becoming encased in flesh to create the paddle-like flippers we see in modern whales. This wasn't simply a matter of adding webbing between existing fingers, but rather a complete restructuring of the entire limb to optimize it for underwater propulsion and steering. Meanwhile, the hind limbs were following the opposite trajectory, becoming smaller and less functional with each passing generation. In the earliest whales like Pachycetus, these legs had been essential for both terrestrial and aquatic locomotion. But as their descendants became more committed to ocean life, the energy costs of maintaining large hind limbs began to outweigh their benefits. Natural selection favored individuals with smaller, more streamlined posterior regions, leading to the gradual reduction and eventual disappearance of external hind limbs. This process wasn't uniform across all whale lineages. Some early whales retained functional hind limbs for millions of years longer than others, suggesting that different species were exploring different solutions to the challenges of aquatic life. The fossil record shows us whales with tiny but still articulated hind legs, whales with hind limbs that had become internal structures invisible from the outside, and whales that had eliminated their posterior limbs entirely. The development of the whale tail represents perhaps the most crucial innovation of this entire evolutionary transformation. Unlike fish, which generate propulsion through side-to-side motion of their tails, whales evolved a vertical tail fluke that moves up and down. This innovation required extensive modifications to the whale spine, creating the flexible, powerful vertebral column that allows modern whales to generate the tremendous forces needed for high-speed swimming and deep diving. The early stages of tail fluke evolution can be traced through the fossil record with remarkable precision. The most primitive whales show no evidence of tail flukes at all, relying instead on their limbs and undulating body motion for propulsion. Gradually, the vertebrae at the end of the tail began to broaden and flatten, providing attachment points for the powerful muscles that would eventually drive the tail fluke. The final tail vertebrae developed special adaptations to support the flukes themselves, creating the distinctive whale tail that has remained virtually unchanged for the past 30 million years. As these anatomical changes were taking place, the global environment was also undergoing significant transformations that would profoundly influence the future course of whale evolution. The warm, stable climate of the early Eocene was giving way to more variable conditions, with periodic cooling events that altered ocean circulation patterns and marine ecosystems. These changes created new challenges for marine life, but they also opened up new opportunities for animals that could adapt quickly to changing conditions. The cooling climate led to the formation of the first permanent ice sheets in Antarctica, which had dramatic effects on global ocean circulation. Cold, nutrient-rich water began to flow from the polar regions toward the equator, creating upwelling zones where deep-sea nutrients were brought to the surface. These areas became incredibly productive, supporting massive populations of plankton and the fish that fed on them. For the evolving whales, these changes represented both a crisis and an opportunity. Species that had been specialized for life in warm tropical seas found themselves struggling to survive in cooler waters with different prey distributions. But those lineages that could adapt to the new conditions discovered vast new feeding grounds that could support much larger populations than had ever been possible before. It was during this period of environmental transition that we begin to see the emergence of the first truly modern whale lineages. The toothed whales, or Odontocetes, began to develop the sophisticated echolocation abilities that would make them the ocean's most efficient predators. The baleen whales, or Mysticetes, started down the evolutionary path, that would eventually lead to filter feeding and the gigantic body sizes we associate with modern great whales. The development of echolocation in toothed whales represents one of the most remarkable examples of convergent evolution in the natural world. Completely independently from bats, which had evolved their own echolocation systems for aerial hunting, whales developed the ability to navigate and hunt using sound waves. This innovation required the evolution of specialized sound-producing organs, sophisticated neural processing systems, and anatomical modifications to focus and direct echolocation calls. The earliest evidence for echolocation in whales comes from fossil skulls that show the characteristic asymmetry associated with this ability in modern species. The development of echolocation was not a sudden event, but rather a gradual process that took millions of years to reach the sophisticated levels we see in contemporary dolphins and porpoises. Early echolocating whales probably had much simpler systems than their modern descendants, perhaps capable of detecting large objects and obstacles, but lacking the fine resolution needed for precise prey capture. The evolution of baleen feeding followed a completely different trajectory, but one that was equally revolutionary in its implications. Rather than developing better ways to catch individual prey items, the ancestors of modern baleen whales evolved the ability to filter enormous quantities of small organisms from the water. This feeding strategy required the development of the baleen plates themselves, flexible structures made of keratin that act like a sieve to separate food from seawater. The transition to filter feeding was not a simple process, and it required extensive modifications to whale anatomy and behavior. The skulls of early baleen whales had to be restructured to accommodate the massive baleen plates and the enormous volumes of water that would need to be processed during feeding. The throat region evolved specialized pleats that could expand dramatically, allowing these whales to take in huge mouthfuls of water and prey. Perhaps most remarkably, this transition to filter feeding ultimately enabled whales to achieve the enormous body sizes that characterize many modern species. By feeding on vast swarms of small organisms rather than individual large prey, baleen whales could access far more energy than would have been possible through conventional predation. This abundance of food would eventually support the evolution of animals like the blue whale, which at over 100 feet in length and 200 tons in weight represents the largest animal that has ever lived on Earth. The story of whale evolution during the late Eocene and early Oligocene periods is one of rapid diversification and experimentation. Fossil sites from around the world reveal a stunning array of whale species, each representing a different solution to the challenges and opportunities of marine life. Some of these lineages would prove to be evolutionary dead ends, while others would give rise to the magnificent diversity of modern cetaceans. The success of whales during this period can be attributed to several key factors that work together to create one of evolution's most remarkable success stories. Their mammalian heritage provided them with advanced nervous systems and sophisticated behaviors that gave them advantages over the reptilian marine predators that had dominated earlier eras. Their warm-blooded metabolism allowed them to remain active in cooler waters and to pursue prey across vast distances. Perhaps most importantly, their social intelligence enabled them to develop complex behaviors and cooperative strategies that multiplied their effectiveness as marine predators. As we trace the evolutionary journey from those early wolf-like creatures wading in ancient rivers to the diverse array of modern whales that populate today's oceans, we see a story that speaks to the incredible adaptability and resilience of life on Earth. The transformation was not always smooth or predictable, and many lineages were lost along the way. But the survivors of this great evolutionary experiment have become some of the most successful and remarkable animals on our planet. The whales that emerged from this crucible of evolutionary change were fundamentally different from their terrestrial ancestors, yet they retained the intelligence, social complexity, and behavioral flexibility that had made mammals successful on land. In adapting to life in the ocean, they didn't simply become aquatic versions of their former selves. Instead, they became something entirely new, marine mammals that combined the best features of their mammalian heritage with revolutionary adaptations for ocean life. The fossil record tells us that by 35 million years ago, the basic body plan of modern whales had been established. These animals possessed the streamlined bodies, powerful tail flukes, and modified respiratory systems that characterize all contemporary cetaceans. Their limbs had been transformed into flippers, their nostrils had migrated to the tops of their heads to form blowholes, and their entire anatomy had been reorganized for efficient movement through water rather than across land. Yet even as the fundamental whale body plan stabilized, evolution continued to refine and perfect these remarkable animals. The cooling climate of the Oligocene epoch created new selective pressures that favored ever more efficient swimming abilities and sophisticated sensory systems. The whales that survived and thrived during this period were those that could dive deeper, swim faster, and detect prey with greater precision than their ancestors. This ongoing refinement of whale anatomy and behavior would continue for millions of years, producing the incredible diversity of modern cetaceans, from the massive blue whales that filter feed on tiny krill to the deep-diving sperm whales that hunt giant squid in the ocean's depths, from the acrobatic dolphins that coordinate their hunts with complex vocalizations to the Arctic-dwelling narwhals with their distinctive tusks. The modern whale family represents one of evolution's greatest success stories. But the true marvel of whale evolution was yet to come. As these early ocean dwellers established themselves in the marine realm, the forces of natural selection began to sculpt them into forms that would have seemed impossible to their terrestrial ancestors. The next chapter of our story unfolds during a period of remarkable innovation, when whales began to develop the extraordinary abilities that make them such successful ocean predators today. Around 30 million years ago, during the early Oligocene period, the descendants of those serpentine basilosaurids faced a changing world. The global climate was cooling, ice was beginning to form at the poles, and the ocean currents that had remained stable for millions of years were shifting into new patterns. These changes brought both challenges and opportunities for marine life, creating new ecological niches that would be filled by increasingly specialized whales. It was during this transformative period that we see the emergence of the two great whale lineages that dominate our modern oceans. The first group, known to scientists as Odontocetes, would become the toothed whales. These animals retained the sharp, pointed teeth of their ancestors, but began to develop something far more remarkable than any terrestrial mammal had ever possessed. The second group, the Mysticetes, took an entirely different evolutionary path, one that would lead them to become the gentle giants we know as baleen whales. The story of how toothed whales developed echolocation reads like science fiction, yet it represents one of nature's most elegant solutions to the challenge of hunting in dark water. Imagine the descendants of Basilosaurus gradually developing the ability to see with sound, creating detailed mental maps of their underwater world, using nothing but acoustic waves. This wasn't a sudden transformation, but rather a gradual refinement that took place over millions of years. The earliest evidence for echolocation in whales comes from fossil skulls that show subtle asymmetries, with one side of the head developing differently from the other. In modern dolphins and porpoises, this asymmetry is pronounced, reflecting the complex arrangement of air sacs and fatty tissues that focus and direct their sonar calls. The fossil record suggests that these structures evolved gradually, beginning as simple sound-producing organs, and eventually becoming the sophisticated biological sonar systems we observe today. The development of echolocation required extensive modifications to whale anatomy. The skull had to be restructured to accommodate the melon, a specialized organ made of fatty tissue that acts like an acoustic lens to focus sound waves. The lower jaw evolved to become a sound-receiving antenna, with acoustic windows that channel returning echoes to the inner ear. Most remarkably, the brain developed new neural pathways capable of processing the complex three-dimensional information contained in these acoustic signals. early echolocating whales probably had much simpler abilities than their modern descendants. They may have been able to detect large obstacles or schools of fish, but likely lacked the precision needed to distinguish between different types of prey or to navigate complex underwater terrain. Over time, natural selection favored individuals with increasingly refined echolocation abilities, leading to the remarkable precision we see in contemporary dolphins, which can echolocate objects as small as coins buried in sand. The evolution of echolocation opened up entirely new hunting opportunities for toothed whales, no longer dependent on visual hunting in the shallow, sunlit waters near shore. These animals could pursue prey into the darkest depths of the ocean. They could hunt at night, in murky water, or in the perpetual darkness of the deep sea, giving them access to food sources that had been unavailable to their ancestors. This acoustic revolution coincided with another crucial development in whale evolution, the refinement of their swimming abilities. The descendants of early whales had inherited a flexible spine and powerful tail fluke, but millions of years of natural selection continued to perfect these structures. The vertebrae became more specialized, with different regions of the spine optimized for different aspects of swimming performance. The tail fluke itself underwent continuous refinement, with the flukes becoming larger and more efficient at generating thrust. The muscles that power these flukes grew stronger and more coordinated, allowing whales to achieve swimming speeds that would have been impossible for their earlier ancestors. Some modern dolphins can reach speeds of over 30 miles per hour, while larger whales can maintain steady cruising speeds that allow them to traverse entire ocean basins during their migrations. The evolution of whale respiratory systems during this period represents another masterpiece of biological engineering. The simple nostrils of Pachychaetus had already begun their migration toward the top of the skull in Ambulocetus, but it would take millions more years for this process to reach completion. The blowhole that characterizes modern whales is far more than just relocated nostrils. It represents a complete reorganization of the whale's respiratory system for efficient breathing at the water's surface. Modern whale blowholes are equipped with powerful muscular valves that can seal the airway completely when the animal dives. These valves are so effective that they can withstand the tremendous pressures encountered in the deep ocean, preventing water from entering the lungs even during the deepest dives. The internal structure of whale lungs also evolved to become more efficient at extracting oxygen from each breath, allowing these animals to hold their breath for extended periods while hunting or traveling underwater. The development of blubber represents yet another crucial adaptation that allowed whales to thrive in their marine environment. This thick layer of fat beneath the skin serves multiple functions, providing insulation against the cold ocean water, storing energy for long migrations, and contributing to the whale's streamlined shape. The evolution of blubber was particularly important as global temperatures began to cool during the Oligocene, allowing whales to expand their range into colder waters that had previously been uninhabitable. Different whale lineages evolved different strategies for dealing with the thermal challenges of ocean life. Some species developed thick blubber layers that allowed them to venture into polar waters, while others remained in tropical and subtropical regions where their thermal needs were less demanding. The distribution of modern whale species still reflects these ancient adaptations, with the largest whales generally found in the coldest waters where their size and blubber provide the greatest advantages. While toothed whales were perfecting their echolocation abilities, the ancestors of modern baleen whales were embarking on an equally remarkable evolutionary journey. Rather than becoming better predators of individual prey items, these whales evolved toward a completely different feeding strategy. They became filter feeders, developing the ability to strain enormous quantities of small organisms from the water. The transition to filter feeding required revolutionary changes to whale anatomy. The sharp teeth that had served their ancestors so well as predators were gradually replaced by baleen plates, flexible structures made of keratin that hang from the upper jaw like a curtain. These plates act as a sophisticated sieving system, allowing water to flow out while retaining small fish, crustaceans, and plankton. The earliest baleen whales still possessed both teeth and primitive baleen plates, suggesting that the transition between predatory and filter feeding strategies was gradual rather than sudden. Over time, the teeth were lost entirely as the baleen plates became more efficient at capturing prey. The skulls of baleen whales became enormous to accommodate these feeding structures, with some modern species having skulls that comprise nearly 1/3 of their total body length. The throat region of baleen whales also underwent dramatic modifications to support their new feeding strategy. Expandable throat pleats evolved that allow these whales to take in massive volumes of water and prey in a single gulp. A feeding blue whale can engulf up to 16,000 gallons of water at once, then use its powerful tongue to push the water out through the baleen plates while retaining the food organisms suspended within. This filter feeding strategy proved to be extraordinarily successful, but it would take millions of years for baleen whales to reach their full potential. The early filter feeders were relatively small animals, perhaps 20 or 30 feet in length, similar in size to modern grey whales. They fed on the abundant small organisms that lived in coastal waters, gradually refining their feeding techniques and expanding their range as ocean conditions changed. The development of different feeding strategies allowed the two major whale lineages to coexist without direct competition. Toothed whales specialized in capturing individual prey items, from small fish and squid to larger marine mammals. Baleen whales focused on filtering vast quantities of small organisms from the water. This division of feeding strategies has persisted to the present day, allowing both groups to thrive in the evolution of whales. During this period represents same ocean environments. The social, another fascinating chapter in their story. As their brains grew larger and more complex, whales began to develop sophisticated social behaviors that enhanced their survival and reproductive success. Early evidence for whale social behavior comes from fossil sites where multiple individuals are found together, suggesting that some species were already living in groups rather than as solitary hunters. The development of complex vocalizations in whales appears to have evolved hand in hand with their social behavior. While the echolocation calls of toothed whales serve primarily for navigation and hunting, many whale species also developed elaborate songs and calls used for communication with other members of their species. These vocalizations can travel for hundreds of miles underwater, allowing whales to maintain contact with family members and potential mates across vast distances. The magnetic sense that allows modern whales to navigate during their long migrations may also have evolved during this period, though the fossil evidence for this ability is indirect. Many contemporary whales undertake journeys of thousands of miles, traveling from feeding areas to breeding grounds with remarkable precision. The ability to sense Earth's magnetic field would have provided these ancient mariners with a reliable navigation system, allowing them to maintain course even when traveling through featureless ocean environments. As whale evolution continued through the Oligocene and into the Miocene periods, approximately 20 to 5 million years ago, we begin to see the emergence of whale species that would be recognizable to modern observers. The fundamental body plan had been established, and natural selection was now fine-tuning the details that would allow different species to exploit specific ecological niches within the marine environment. During this period, the first true deep-diving whales appeared in the fossil record. These animals had evolved the physiological adaptations necessary to withstand the crushing pressures of the deep ocean, including specialized blood chemistry that allowed them to store more oxygen and circulatory systems that could redirect blood flow during extended dives. The sperm whales that hunt giant squid in today's oceans are the descendants of these early deep-sea specialists. The diversification of whale species during the Miocene was driven in part by the continued cooling of global climate and the associated changes in ocean circulation patterns. As ice sheets expanded at both poles, cold, nutrient-rich water began to flow from polar regions toward the equator, creating highly productive upwelling zones where marine life flourished. These areas became focal points for whale evolution, supporting large populations that could sustain the development of new species and feeding strategies. The formation of the Isthmus of Panama during this period had profound effects on global ocean circulation and whale evolution. The closing of the connection between the Atlantic and Pacific Oceans altered current patterns and created new barriers to whale migration. Some whale populations became isolated on opposite sides of the newly formed land bridge, leading to the evolution of distinct species adapted to different ocean basins. The Arctic Ocean became increasingly important as a whale habitat during the later stages of the Miocene, as cooling temperatures created seasonal ice formations that supported unique marine ecosystems. The ancestors of modern bowhead whales and other Arctic specialists evolved adaptations that allowed them to thrive in these challenging environments, including reinforced skulls capable of breaking through ice and feeding strategies optimized for the short Arctic summer when food is abundant. The tropical and subtropical oceans also supported diverse whale communities during this period, with different species specializing in hunting the various prey that inhabited warm water ecosystems. The ancestors of modern pilot whales and false killer whales evolved to hunt deep-water squid, while other lineages focused on catching fish in shallow coastal waters or feeding on the abundant plankton that bloomed in tropical seas. The evolution of whale migration patterns during this period represents one of the most remarkable aspects of their adaptation to marine life. As seasonal changes became more pronounced due to global cooling, whales evolved the ability to undertake journeys of thousands of miles to take advantage of feeding opportunities in different parts of the ocean. These migrations required not only the physical stamina to swim vast distances, but also sophisticated navigation abilities and the social organization necessary to coordinate group movements. The metabolic adaptations that support these long migrations are among the most impressive features of whale physiology. Modern baleen whales can fast for months during their breeding seasons, living entirely off energy stored in their blubber while traveling between feeding and breeding areas. This ability to store and utilize energy efficiently was crucial to the success of migratory whale species and represents millions of years of evolutionary refinement. The development of whale breeding behaviors during this period also shows remarkable sophistication. Many whale species evolved complex mating systems that involve elaborate courtship displays, competitive interactions between males, and sophisticated parental care behaviors. The songs of humpback whales, which can last for hours and travel across entire ocean basins, represent one of the most complex acoustic displays in the animal kingdom. The intelligence that characterizes modern whales also appears to have reached advanced levels during this period of evolution. Whale brains grew larger relative to their body size, and the areas responsible for complex cognitive functions became more developed. Evidence for advanced intelligence in fossil whales is indirect, but the sophisticated behaviors of modern species suggest that high-level cognitive abilities evolved relatively early in whale evolutionary history. The sensory abilities of whales continued to evolve and diversify during this period, with different species developing specialized adaptations for their particular lifestyles and habitats. Deep-diving whales evolved enhanced pressure tolerance and modified visual systems for hunting in the permanent darkness of the deep ocean. Shallow water species maintained keen eyesight for visual hunting, while developing enhanced acoustic abilities for communication and navigation. The evolution of whale immune systems during this period represents another crucial adaptation to marine life. The ocean environment presents unique challenges in terms of disease and parasites, and whales evolved sophisticated immune responses to deal with these threats. The ability to maintain health while living in close contact with seawater and the various organisms it contains was essential to the success of marine mammals. As we trace the evolution of whales through these millions of years of gradual change and adaptation, we see a story of remarkable resilience and creativity. Each environmental challenge was met with evolutionary innovations that not only allowed whales to survive, but to thrive in ways that exceeded what had been possible for their terrestrial ancestors. The ocean, which had initially represented a new frontier for mammals to explore, became a realm where they achieved some of their greatest evolutionary successes. The whales that emerged from this long process of adaptation were fundamentally different from any animals that had existed before. They combined the intelligence and behavioral complexity of advanced mammals with anatomical and physiological adaptations that made them supremely effective marine predators and filter feeders. Their success in the ocean land animal, while to sizes that dwarfed any, would eventually allow them to grow, maintaining the social complexity and cognitive abilities that distinguished them from other marine life. The story of whale evolution during these crucial millions of years demonstrates the power of gradual change to produce extraordinary results. Each generation built upon the adaptations of the previous one, with natural selection continuously refining and improving the whale body plan. The cumulative effect of these small changes over vast periods of time was the transformation of wolf-like terrestrial mammals into the magnificent marine creatures we know today. As global climate continued to fluctuate during the late Miocene and into the Pliocene, whales faced new challenges that would test the effectiveness of their evolutionary adaptations. The continued cooling of ocean temperatures and the increasing seasonality of marine productivity created selective pressures that favored ever more efficient feeding strategies and migration patterns. It was during this period that some whale lineages began the evolutionary journey that would lead to the massive sizes we see in modern great whales. The transformation toward gigantism in baleen whales represents one of evolution's most spectacular achievements, yet it would not occur for millions of years after these early filter feeders first appeared. During the Pliocene epoch, roughly 5 to 3 million years ago, the ancestors of modern great whales were still relatively modest in size, measuring perhaps 30 to 40 feet in length. They lived in oceans that were becoming increasingly productive due to changing climate patterns. But the ecological conditions necessary to support truly massive marine animals had not yet emerged. The key to understanding whale gigantism lies in recognizing how oceans' food webs were profoundly transformed during this period. As global temperatures continued to cool and ice sheets expanded at both poles, new patterns of ocean circulation emerged that would revolutionize marine ecosystems. Cold, nutrient-rich water from the polar regions began to flow more vigorously toward the equator, creating powerful upwelling currents that brought deep-sea minerals to the surface waters where sunlight could fuel photosynthesis. These upwelling zones became biological gold mines, supporting explosive blooms of phytoplankton that formed the base of incredibly productive food chains. Tiny crustaceans like krill multiplied in vast swarms that could extend for miles across the ocean surface, creating dense patches of food that had never existed in such abundance before. For filter-feeding whales, these developments represented an unprecedented opportunity to access enormous quantities of high-energy prey. The evolutionary response durable. Natural to this bounty was gradual, but index selection began to favor baleen whales with larger mouths capable of processing greater volumes of water and prey. Generation by generation, these animals grew bigger, their feeding apparatus became more efficient, and their capacity for storing energy in the form of blubbering creasels that could dramatically, the WHD take advantage of the richest feeding areas, would have significant advantages in terms of survival and reproductive success. The development of gulp feeding in the ancestors of modern rorquals represents one of the most remarkable feeding innovations in the animal kingdom. Rather than swimming slowly through the water with their mouths open like modern right whales, these advanced filter feeders evolved the ability to accelerate rapidly toward concentrations of prey, opening their enormous mouths to engulf massive volumes of water and krill in a single feeding unge. This feeding strategy required extensive to whale modifications anatomy. The throat pleats that had evolved in earlier baleen whales became more numerous and more expandable, allowing the mouth cavity to increase in volume by several times. The tongue evolved into a massive muscular structure capable of forcing hundreds of tons of water out-aining the food organisms suspended within. Through the baleen plates, while Rhett's lower jaw became extraordinarily flexible, with special joints that allowed it to dislocate slightly during feeding lunges. The cardiovascular system of these growing whales also underwent remarkable changes to support their increasingly energetic feeding behavior. The heart became proportionally larger and more powerful, capable of pumping blood through a circulatory system that might extend for hundreds of feet in the largest individuals. Specialized blood vessels evolved that could constrict during deep dives, redirecting blood flow to essential organs while conserving oxygen for extended periods underwater. The respiratory system of giant whales represents another masterpiece of evolutionary engineering. The lungs became more efficient at extracting oxygen from each breath, while the blood developed enhanced capacity for storing and transporting oxygen throughout the massive body. These adaptations allowed large whales to hold their breath for extended periods while pursuing prey at depth, despite their enormous metabolic requirements. The evolution of whale migration patterns during this period of increasing body size represents one of nature's most impressive logistical achievements. As these animals grew larger, their energy requirements increased dramatically, but so did their capacity for long-distance travel. The largest whales evolved the ability to undertake journeys of thousands of miles between feeding and breeding areas, following seasonal patterns of food availability across entire ocean basins. These migrations required not only physical endurance, but also sophisticated navigation abilities. Modern whales appear to use a combination of magnetic sensing, celestial navigation, and acoustic landmarks to find their way across featureless ocean expanses. The evolution of these navigation systems during the Pliocene and Pleistocene periods allowed whales to exploit feeding opportunities that were separated by vast distances, making their gigantic body sizes energetically viable. The social implications of increasing whale size were equally profound. Larger whales could produce louder vocalizations that traveled farther underwater, allowing them to maintain contact with family members and potential mates across greater distances. The songs of humpback whales, which can be heard by other whales hundreds of miles away, evolved during this period as these animals grew large enough to generate the powerful acoustic signals necessary for long-distance communication. The breeding behaviors of large whales also became more elaborate during this evolutionary period. The enormous energy investment required to produce and raise whale calves meant that reproductive success became increasingly critical to individual fitness. Competition between males intensified, leading to the evolution of complex mating displays and aggressive behaviors that required significant physical strength and endurance. The development of whale intelligence during the transition to gigantism represents another fascinating aspect of their evolution. As whale brains grew larger in absolute size along with their bodies, these animals developed increasingly sophisticated cognitive abilities. The complex social behaviors, problem-solving skills, and cultural transmission of knowledge that characterize modern great whales appear to have evolved in parallel with their increasing body size. The relationship between whale size and intelligence is not simply a matter of larger brains containing more neurons. The social and environmental challenges faced by giant marine mammals required new types of cognitive abilities that had not been necessary for smaller species. The ability to remember feeding areas across vast ocean basins, to coordinate group feeding behaviors, and to maintain social relationships with individuals encountered infrequently over enormous territories, all required advanced mental capacities. The acoustic world of giant whales became increasingly complex as their size increased. Larger whales could produce lower frequency sounds that traveled farther through the ocean, opening up new possibilities for long-distance communication and echolocation. The infrasonic calls of blue whales, which operate below the range of human hearing, can travel across entire ocean basins under the right conditions, allowing these massive animals to maintain acoustic contact across distances that would have been impossible for smaller species. The evolution of specialized feeding areas and the seasonal movements between them created new selective pressures that further refined whale anatomy and behavior. Different populations of the same species began to specialize in exploiting particular feeding grounds, leading to subtle but important differences in feeding techniques, migration routes, and social behaviors. These population-specific adaptations would eventually contribute to the speciation processes that produce the diversity of modern great whales. The impact of increasing whale size on ocean ecosystems was profound and far-reaching. Giant whales became keystone species in marine food webs, their feeding activities helping to distribute nutrients throughout the ocean column. When these massive animals dive to feed and then return to the surface to breathe, they transport nutrients from deep water to surface layers, fertilizing the phytoplankton communities that form the base of marine food chains. The waste products of large whales also became important sources of nutrients for marine ecosystems. The fecal plumes of feeding whales provide essential nutrients for plankton communities, while whale carcasses that sink to the deep ocean floor create unique ecosystems that can persist for decades. The evolution of whale gigantism thus had cascading effects throughout marine environments, influencing the distribution and abundance of countless other species. The thermal challenges faced by increasingly large whales required continued refinement of their insulation and metabolic systems. Larger body size provided advantages in terms of heat retention due to the favorable surface area to volume ratio, but it also created new problems in terms of heat dissipation during periods of intense activity. The blubber layer became more sophisticated, with different regions specialized for insulation, energy storage, and hydrodynamic efficiency. The skeletal system of giant whales underwent remarkable adaptations to support their massive body weight, while maintaining the flexibility necessary for efficient swimming. The vertebral column became more robust, while retaining the flexibility needed for the undulating swimming motion that powers whale locomotion. The ribs evolved to be more flexible, allowing the chest cavity to compress during deep dives while providing structural support during surface activities. The digestive system of large baleen whales became increasingly specialized for processing enormous quantities of small prey organisms. The stomach evolved into a complex multi-chambered structure capable of handling the massive volumes of food consumed during feeding lunges. The intestinal system became proportionally longer, maximizing the extraction of nutrients from the huge quantities of krill and small fish that formed the bulk of their diet. The immune system of giant whales also required special adaptations to function effectively in animals with such enormous body sizes. The lymphatic system became more extensive and complex, while specialized immune organs evolved to monitor and protect the vast internal spaces of these marine giants. The ability to maintain health and resist disease became increasingly critical as whale body size increased, since infections or other health problems could have devastating effects on such large organisms. The evolutionary arms race between whales and their prey also intensified during the period of increasing body size. As whales became more efficient predators, capable of consuming vast quantities of krill and small fish, these prey species evolved new strategies for avoiding capture. Krill developed more sophisticated swarming behaviors and seasonal migration patterns, while small schooling fish evolved enhanced sensory systems for detecting approaching whales. The coevolution between whales and their prey created increasingly complex predator-prey dynamics that influenced the structure of entire marine ecosystems. The seasonal movements of whale populations began to track the availability of prey species, creating predictable patterns of predation pressure that shaped the evolution and distribution of numerous marine organisms. These interactions became so tightly coupled that changes in whale populations could have dramatic effects on the abundance and behavior of their prey species. The development of different feeding strategies among various whale lineages during this period of gigantism led to the evolution of distinct ecological niches within marine environments. Some species specialized in feeding on surface swarms of krill, while others developed techniques for capturing prey at greater depths. Still others evolved to feed primarily on small schooling fish, requiring different hunting strategies and anatomical adaptations. The geographic distribution of giant whales became increasingly tied to the locations of the most productive feeding areas in the world's oceans. The Antarctic region, with its massive seasonal blooms of krill, became a crucial feeding ground for many of the largest whale species. The Arctic Ocean, with its own unique patterns of seasonal productivity, supported different communities of large whales adapted to the specific conditions of polar environments. The tropical and subtropical oceans, while less productive than polar regions, continued to support populations of large whales that had evolved different feeding strategies. Some species became specialists in capturing deep-water prey that migrated to surface waters at night, while others focused on the patchy but rich feeding opportunities provided by upwelling zones along continental margins. The evolution of whale gigantism was not uniform across all lineages. While some species grew to enormous sizes, others remained smaller and more specialized for particular ecological niches. The diversity of modern whale species reflects this evolutionary diversification, with animals ranging from relatively small minke whales to the massive blue whales that represent the pinnacle of vertebrate gigantism. The physiological constraints that ultimately limit whale size became apparent during this evolutionary expansion. The largest whales approached the theoretical limits imposed by the physics of filter feeding and the metabolic requirements of maintaining such enormous bodies. The blue whale, at over 100 feet in length and weighing up to 200 tons, represents perhaps the largest size that is possible for a filter-feeding marine mammal, given the current productivity of ocean ecosystems. The social structures of giant whales evolved to accommodate the unique challenges and opportunities presented by their enormous size. Family groups became more dispersed across vast ocean areas, with individuals maintaining contact through long-distance vocalizations rather than close physical proximity. The social bonds between mothers and calves became even more critical, as young whales required extended periods of parental care to develop the skills and knowledge necessary for survival in the open ocean. The cultural transmission of knowledge became increasingly important in whale societies as their size and mobility increased. Information about feeding areas, migration routes, and seasonal patterns had to be passed from generation to generation to ensure the survival of whale populations. This cultural knowledge became as important as genetic adaptations in determining the success of different whale lineages. The impact of whale gigantism on human cultures and maritime activities would not become apparent for millions of years, but the evolution of these massive marine mammals during the Pliocene and Pleistocene periods set the stage for some of the most dramatic encounters between humans and wildlife in recorded history. The whales that emerged from this evolutionary crucible were unlike anything that had ever existed before, combining intelligence, size, and grace in ways that would capture the human imagination for millennia to come. As we consider the remarkable transformation that led from small, early filter feeders to the magnificent giants that populate our modern oceans, we see a story of evolutionary innovation and environmental opportunity converging to produce some of the most spectacular animals on Earth. The cooling climate and changing ocean circulation patterns of the late Cenozoic era created conditions that favored the evolution of gigantism in marine mammals, leading to the emergence of creatures that push the boundaries of what is physiologically possible for living organisms. The whales that achieved these enormous sizes did not do so in isolation, but as part of complex evolutionary relationships with their prey, their physical environment, and each other. Their success represents not just individual adaptation, but the evolution of entire ecosystems organized around the presence of these massive marine predators and filter feeders. The ocean environments that support modern great whales are fundamentally different from those that existed before the evolution of whale gigantism, shaped by millions of years of coevolution between whales and their marine communities. The story of whale evolution from the Eocene to the present day represents one of the most complete and well-documented examples of major evolutionary transition in the fossil record. From the wolf-like Pachycetus hunting fish in ancient rivers to the massive blue whales that cruise our modern oceans. This transformation demonstrates the remarkable power of natural selection to reshape organisms in response to new environmental opportunities and challenges. The journey from land to sea that whales completed over 50 million years ago required innovations in anatomy, physiology, behavior, and ecology that rival any evolutionary achievement in the history of life on Earth. These marine mammals succeeded in becoming not just aquatic, but supremely aquatic, developing capabilities that exceed those of animals that had never left the ocean in the first place. The intelligence and social complexity that whales retained from their mammalian heritage, combined with their remarkable adaptations for marine life, created animals that are both alien and familiar to human observers. They represent a different solution to the challenge of complex life, one that took a path through the ocean rather than remaining on land. Their success demonstrates that intelligence and social cooperation can flourish in environments very different from those in which these traits originally evolved. The conservation challenges facing modern whales remind us that even the most successful evolutionary stories can be interrupted by rapid environmental changes. The whales that survived ice ages, volcanic eruptions, and massive shifts in ocean chemistry now face new challenges from human activities that are altering ocean environments faster than evolutionary processes can respond. Understanding their remarkable evolutionary history provides crucial context for appreciating both their resilience and their vulnerability in our rapidly changing world. As we reflect on the extraordinary journey that transformed terrestrial mammals into the largest animals ever to exist on Earth, we are reminded that evolution is not a process that occurs in isolation from environmental change. The whales of today are the products of millions of years of interaction between changing climates, shifting ocean currents, and the relentless creativity of natural selection. Their story continues to unfold in our modern oceans, where they face new challenges that will test the adaptations forged over countless generations of evolutionary refinement. The legacy of whale evolution extends far beyond the animals themselves, influencing our understanding of how life responds to environmental change and how complex organisms can undergo radical transformations while retaining their essential characteristics. The whales that return to the sea carry with them the genetic memory of their terrestrial past, yet they have become something entirely new, creatures perfectly adapted for a life spent between the ocean depths and the surface of an ever-changing world. In the quiet depths where these magnificent animals now make their home, the echoes of their evolutionary journey continue to resonate. Each dive they take, each song they sing, each breath they draw at the ocean's surface represents the culmination of one of evolution's greatest experiments. They are living proof that life finds a way not just to survive, but to flourish, creating beauty and complexity that exceeds our wildest imagination. The whales that grace our modern oceans are the inheritors of an evolutionary legacy that spans geological ages. They carry within their massive frames the story of life's remarkable ability to reinvent itself, to explore new possibilities, and to create forms of existence that push the boundaries of what seems possible. Their presence in our world is a testament to the power of gradual change to produce extraordinary results, and a reminder that the natural world continues to hold surprises that can inspire wonder and humility in equal measure. As these gentle giants continue their ancient migrations across ocean basins that their ancestors helped to shape, they carry with them the wisdom of millions of years of evolutionary experience. They are ambassadors from a deep past, representatives of alternative possibilities for complex life, and guardians of ocean realms that remain largely mysterious to those of us bound to the land. Their story of return to the sea reminds us that home is not always where life begins, but sometimes where it finds its truest expression. The story of whale evolution reaches perhaps its most fascinating chapter during the Miocene epoch, roughly 20 million years ago, when the descendants of those early ocean pioneers began to diverge into the two great lineages that would define the future of marine mammal life. The world's oceans had become cooler and more stratified, creating distinct layers of water with different temperatures and nutrient concentrations. These changes in ocean structure would profoundly influence how whales would continue to evolve and adapt to their aquatic environment. In the deeper, darker waters of these ancient seas, some whale lineages were developing capabilities that seem almost supernatural to our modern understanding. The ancestors of what we now call toothed whales were beginning to experiment with using sound not just for communication, but as a tool for navigation and hunting. This represents one of evolution's most remarkable innovations, the development of biological sonar that would eventually surpass even our most sophisticated human technology. The earliest evidence of echolocation in whales appears in fossil skulls from this period, where we can observe subtle but significant changes in bone structure. The skull begins to show asymmetry, with one side developing differently from the other. This seemingly minor change reflects the beginning of a complex system that would allow whales to perceive their underwater world through sound waves rather than relying solely on vision. Imagine swimming in the perpetual twilight of the deep ocean, where sunlight fades to nothing within a few hundred feet of the surface. In this alien environment, the ability to see becomes far less important than the ability to hear and interpret the acoustic landscape. The early echolocating whales discovered that sound travels much faster and farther in water than in air, opening up possibilities for perception that their terrestrial ancestors could never have imagined. The development of echolocation required extensive modifications to whale anatomy. Specialized fatty tissues began to evolve in the forehead region, creating what scientists now call the melon. This organ acts like a biological acoustic lens, focusing sound waves into directed beams that can be aimed at specific objects or areas of interest. The precision of this system is extraordinary, allowing modern dolphins to distinguish between objects that differ by only a few inches in size, even in complete darkness. The lower jaw also underwent remarkable changes during this evolutionary period. Rather than simply supporting teeth for feeding, the jaw became a sophisticated sound-receiving antenna. Acoustic windows evolved along the jawbone, creating pathways for sound waves to travel directly to the inner ear. The brain developed new neural pathways capable of processing the complex three-dimensional information contained in returning sound waves, creating mental maps of unprecedented detail and accuracy. These changes did not happen overnight. The fossil record suggests that early echolocating whales had much simpler abilities than their modern descendants. They could probably detect large obstacles and concentrations of fish, but lacked the precision needed for the sophisticated hunting strategies we observe in contemporary dolphins and porpoises. Each generation built upon the acoustic abilities of the previous one, with natural selection favoring individuals who could echolocate with greater accuracy and range. The evolution of echolocation opened up entirely new ecological niches for toothed whales. They could hunt in complete darkness, pursue prey into deep ocean trenches, and navigate through complex underwater terrain that would have been impossible to traverse using vision alone. Some lineages specialized in hunting squid in the deepest parts of the ocean, while others focused on catching fish in the mid-water column where light barely penetrates. While toothed whales were perfecting their acoustic abilities, another group of whales was taking a completely different evolutionary path. The ancestors of modern baleen whales were developing an entirely different approach to marine life, one that would eventually allow them to become the largest animals ever to exist on Earth. Rather than becoming better at catching individual prey items, these whales evolved toward filter feeding, developing the ability to process enormous volumes of water to extract the small organisms suspended within. The transition to filter feeding began gradually, with early baleen whales still possessing both teeth and primitive filtering structures. Over millions of years, the teeth were gradually lost as the baleen plates became more efficient at capturing prey. These plates, made of keratin like our fingernails and hair, hang from the upper jaw like a flexible curtain. creating a sophisticated sieving system that allows water to flow out while retaining food organisms. The skulls of baleen whales underwent dramatic changes to accommodate this new feeding strategy. They became enormous, with some modern species having skulls that comprise nearly 1/3 of their total body length. The jaw joints evolved special adaptations that allow the mouth to open to incredible angles, while the throat developed expandable pleats that can increase the mouth cavity's volume by several times during feeding. The tongue of baleen whales evolved into one of the most powerful muscular structures in the animal kingdom. In the larger species, the tongue can weigh as much as an elephant and has the strength to force hundreds of tons of water out through the baleen plates while retaining the tiny organisms suspended within. This feeding system is so efficient that a blue whale can consume up to 4 tons of krill in a single day during the peak feeding season. The development of different feeding strategies allowed toothed and baleen whales to coexist in the same ocean environments without direct competition. Toothed whales specialized in pursuing individual prey items, from small fish and squid to larger marine mammals. Baleen whales focused on filtering vast quantities of small organisms from the water. This division of ecological roles has persisted to the present day, allowing both groups to thrive in overlapping marine habitats. The social implications of these evolving feeding strategies were profound. Toothed whales developed increasingly complex social behaviors that enhanced their hunting success. Some species began to hunt cooperatively, using coordinated movements and vocalizations to herd schools of fish or surround individual prey. The intelligence required for such cooperation drove the evolution of larger, more complex brains capable of sophisticated communication and planning. Baleen whales, while generally less social than their toothed relatives, also developed remarkable behaviors related to their feeding strategies. Some species learned to work together during feeding, creating coordinated feeding formations that maximize the efficiency of their filter feeding. Others developed elaborate migration patterns that allowed them to follow seasonal blooms of plankton across vast ocean distances. The evolution of whale migration during this period represents one of nature's most impressive logistical achievements. As ocean productivity became more seasonal and patchy due to changing climate patterns, whales evolved the ability to undertake journeys of thousands of miles to follow food sources or reach suitable breeding areas. These migrations required not only physical endurance, but also sophisticated navigation abilities that allowed whales to find their way across seemingly featureless ocean expanses. Modern whales appear to navigate using a combination of magnetic sensing, celestial navigation, and acoustic landmarks. The ability to detect Earth's magnetic field provides a reliable compass system, while the position of the sun and stars offers additional navigational references. Underwater sound channels created by temperature and salinity differences allow whales to use acoustic beacons that can be detected from hundreds of miles away. The development of these navigation systems was crucial to the success of migratory whale species. The ability to reliably find rich feeding areas or suitable breeding grounds meant the difference between survival and extinction for populations that had become dependent on resources separated by vast distances. The precision of modern whale navigation is extraordinary, with individuals returning to the same feeding areas year after year with remarkable accuracy. The physiological adaptations required for long-distance migration continued to refine whale anatomy during this evolutionary period. The heart became proportionally larger and more efficient, capable of maintaining circulation during extended periods of swimming. The muscles developed enhanced capacity for storing oxygen and metabolizing fat, allowing whales to undertake journeys lasting several months while feeding minimally or not at all. The blubber layer became increasingly sophisticated during this period, serving multiple functions beyond simple insulation. Different regions of the blubber evolved specialized properties, with some areas optimized for energy storage, others for hydrodynamic efficiency, and still others for thermal regulation. The distribution and thickness of blubber became species-specific, reflecting the different thermal challenges faced by whales in various ocean environments. The respiratory system of whales continued to evolve during this period of increasing specialization. The blowhole, which had been gradually migrating from the tip of the snout toward the top of the head, reached its final position in most lineages. This relocation was accompanied by the evolution of powerful muscular valves that could seal the airway completely during dives, preventing water from entering the lungs even under extreme pressure. The lungs themselves became more efficient at extracting oxygen from each breath, while the blood evolved enhanced capacity for storing and transporting oxygen throughout the body. These adaptations allowed whales to hold their breath for extended periods, while diving to great depths in search of food or to avoid predators at the surface. The diving abilities of whales during this evolutionary period began to approach the extraordinary levels we observe in modern species. Some lineages developed the ability to dive to depths of several thousand feet, entering regions of the ocean that had been inaccessible to their ancestors. These deep diving specialists evolved specialized blood chemistry that prevented nitrogen narcosis and other pressure-related problems that would be fatal to most mammals. The sensory world of whales continued to expand and diversify during this period of specialization. Deep diving species evolved enhanced pressure tolerance and modified visual systems capable of functioning in the permanent darkness of the deep ocean. Some developed enlarged eyes with enhanced light-gathering ability, while others reduced their reliance on vision entirely, depending instead on echolocation and other senses. The thermal challenges faced by whales in different ocean environments drove continued refinement of their temperature regulation systems. Arctic species evolved thicker blubber and modified circulatory systems that prevented heat loss in near-freezing water. Tropical species developed different adaptations, including behavioral strategies for avoiding overheating during periods of intense activity. The evolution of whale reproduction during this period shows remarkable adaptations to the challenges of marine life. Gestation periods became extended, allowing whale calves to develop to a more advanced state before birth. The milk produced by whale mothers became incredibly rich in fat, providing the rapid growth necessary for young whales to develop the blubber layer, essential for survival in cold ocean water. Parental care behaviors became increasingly sophisticated, with mothers teaching their calves not only basic survival skills, but also complex cultural knowledge about migration routes, feeding areas, and social behaviors. This cultural transmission of information became as important as genetic inheritance in determining the success of whale populations. The acoustic world of whales became increasingly complex during this period of evolutionary diversification. Different species developed distinct vocal repertoires that served various functions, from long-distance communication to echolocation to courtship displays. The songs of humpback whales, which can last for hours and evolve over time within populations, represent one of the most sophisticated acoustic displays in the animal kingdom. The evolution of whale intelligence during this period reflects the increasing complexity of their social and environmental challenges. Brain size increased both absolutely and relative to body size, with particular expansion in areas associated with acoustic processing, spatial memory, and social cognition. The cognitive abilities of modern whales, including problem-solving skills, tool use, and cultural learning, appear to have emerged during this crucial evolutionary period. The immune system of whales also underwent significant adaptations during this period of specialization. The marine environment presents unique challenges in terms of pathogens and parasites, and whales evolved sophisticated immune responses to deal with these threats. The ability to maintain health while living in constant contact with seawater and the diverse microbial communities it contains was essential to their success as marine mammals. The relationship between whales and their prey became increasingly complex during this evolutionary period. As whales became more efficient predators and filter feeders, their prey species evolved new strategies for avoiding capture, This created an evolutionary arms race that drove innovation on both sides, leading to increasingly sophisticated predator-prey interactions that shaped the structure of marine ecosystems. The coevolution between whales and their prey had far-reaching effects on ocean environments. The feeding activities of large whale populations helped to distribute nutrients throughout the water column, fertilizing plankton communities and supporting the productivity of marine food webs. The waste products of whales became important sources of nutrients for marine ecosystems, while whale carcasses that sank to the deep ocean floor created unique biological communities that could persist for decades. The seasonal patterns of whale feeding and migration began to influence the timing of biological processes throughout marine ecosystems. Plankton blooms, fish spawning, and the life cycles of countless marine organisms became synchronized with the movements of whale populations. These relationships became so tightly coupled that changes in whale abundance could have cascading effects throughout entire ocean basins. The geographic distribution of whale species during this period reflected the increasing specialization of different lineages. Some species became restricted to specific ocean basins or temperature zones, while others developed the ability to cross between different marine environments. The formation of new ocean currents and the gradual cooling of polar regions created barriers and opportunities that influenced whale distribution patterns that persist to this day. The Arctic Ocean became increasingly important as a whale habitat during this period, as cooling temperatures created seasonal ice formations that supported unique marine ecosystems. The ancestors of modern bowhead whales and other Arctic specialists evolved adaptations that allowed them to thrive in these challenging environments, including reinforced skulls capable of breaking through ice and feeding strategies optimized for the brief Arctic summer. The tropical oceans continue to support diverse whale communities, but with different species specializing in the unique opportunities provided by warm water environments. Some became experts at hunting deep water prey that migrated to the surface at night, while others focused on the rich but patchy feeding opportunities provided by upwelling zones along continental margins. The evolution of whale behavior during this period shows increasing sophistication in response to environmental challenges. Some species developed complex seasonal routines that maximized their access to food resources while minimizing energy expenditure during travel between feeding and breeding areas. Others evolved flexible strategies that allowed them to adapt to changing conditions within their lifetimes. The cultural aspects of whale behavior became increasingly important during this evolutionary period. Different populations of the same species began to develop distinct traditions in feeding techniques, migration routes, and social behaviors. These cultural differences were passed from generation to generation through learning and imitation, creating regional variations that enhance the survival of whale populations in different environments. The impact of whale evolution on global ocean chemistry became apparent during this period. The feeding activities of large whale populations helped to transport nutrients from deep water to the surface, enhancing the productivity of marine ecosystems. The carbon sequestration effects of whale populations also became significant, as these large animals stored substantial amounts of carbon in their bodies and transported it to deep ocean environments when they died. The diversity of whale species reached remarkable levels during this period of evolutionary innovation. Fossil sites from around the world reveal an extraordinary array of whale forms, from giants that rivaled modern blue whales to smaller, more agile species adapted for life in coastal environments. Each species represented a different solution to the challenges and opportunities of marine life. The success of whales during this period can be attributed to their remarkable combination of mammalian intelligence and specialized marine adaptations. Their warm-blooded metabolism allowed them to remain active in cold water and to undertake long migrations that would have been impossible for cold-blooded marine animals. Their advanced nervous systems enabled complex behaviors and social cooperation that multiplied their effectiveness as marine predators and filter feeders. The evolution of whale sensory systems reached new levels of sophistication during this period. Some species developed the ability to detect prey at distances of several miles using echolocation, while others evolved enhanced visual systems for hunting in the dim light of deep ocean environments. The integration of multiple sensory systems allowed whales to perceive their underwater world with unprecedented detail and accuracy. The mechanical properties of whale locomotion continued to be refined during this evolutionary period. The tail flukes became more efficient at generating thrust, while the body shape was streamlined to reduce drag during high-speed swimming. Some species evolved the ability to achieve remarkable speeds, while others optimized their locomotion for energy efficiency during long migrations. The thermal physiology of whales became increasingly sophisticated as different species adapted to life in various ocean environments. Countercurrent heat exchange systems evolved that allowed whales to maintain core body temperature while allowing extremities to cool, reducing heat loss in cold water. These adaptations were particularly important for species that ventured into polar regions or dove to great depths where temperatures approach freezing. The reproductive strategies of whales continued to evolve in response to the unique challenges of marine life. Extended gestation periods allowed whale calves to reach a more advanced developmental stage before birth, increasing their chances of survival in the demanding ocean environment. The evolution of extremely rich milk enabled rapid growth of young whales, allowing them to quickly develop the size and blubber reserves necessary for independent survival. The social structures of whale communities became increasingly complex during this period of evolutionary diversification. Some species developed elaborate hierarchical systems that coordinated group activities and resource sharing. Others evolved more egalitarian social structures that emphasize cooperation and mutual support. These social adaptations enhanced the survival and reproductive success of whale populations in challenging marine environments. The communication systems of whales reached extraordinary levels of complexity during this evolutionary period. Long-distance vocalizations allowed individuals to maintain contact across vast ocean distances, while more subtle acoustic signals facilitated coordination during feeding and social activities. The evolution of dialect differences between whale populations created acoustic signatures that helped individuals identify members of their own community. The cognitive abilities of whales expanded dramatically during this period, with evidence of advanced problem-solving skills, tool use, and cultural learning appearing in the fossil and behavioral record. The large brains of whales, with their highly developed cerebral cortex, enabled complex mental processes that rivaled those of the most intelligent terrestrial mammals. The environmental sensitivity of whales became increasingly refined during this evolutionary period. The ability to detect subtle changes in water temperature, salinity, and chemical composition allowed whales to locate productive feeding areas and navigate complex ocean environments. Some species developed the ability to predict seasonal changes in food availability, timing their migrations to coincide with peak feeding opportunities. The relationship between whale evolution and global climate change became increasingly apparent during this period. As ocean temperatures and circulation patterns continued to shift in response to changing atmospheric conditions, whale populations adapted through both evolutionary and behavioral responses. Some species expanded their ranges into newly available habitats, while others became more specialized for particular environmental conditions. The mechanical efficiency of whale swimming continued to improve through this evolutionary period, with refinements in body shape, fin design, and muscle architecture that enhanced performance in various aspects of aquatic locomotion. Some species became specialists in sustained swimming over long distances, while others evolved for burst speed and maneuverability in hunting situations. The diving physiology of whales reached remarkable levels of sophistication, with some species developing the ability to dive to depths exceeding 6,000 feet and remain submerged for over an hour. These extreme diving abilities opened up access to deep-sea food resources that were unavailable to other marine mammals, providing evolutionary advantages that drove further specialization in deep-water environments. The evolution of whale metabolism during this period shows adaptations for the feast or famine lifestyle imposed by seasonal food availability and long migrations. The ability to store large amounts of energy in blubber and to metabolize these reserves efficiently during periods of reduced feeding became crucial to the success of many whale species. The sensory integration capabilities of whales became increasingly sophisticated, with the brain developing enhanced abilities to process and combine information from multiple sensory systems. This integration allowed whales to create detailed mental maps of their environment and to make complex decisions about feeding, migration, and social behavior based on multiple sources of information. The impact of whale behavior on marine ecosystems became more pronounced during this evolutionary period. The feeding activities of whale populations created distinct patterns of nutrient distribution and plankton productivity that influenced the structure of entire food webs. The predictable movements of migrating whales became incorporated into the life cycles of numerous marine organisms. As we trace the continuing evolution of whales through these millions of years of refinement and specialization, we see animals that had become supremely adapted to life in virtually every marine environment on Earth. From the ice-covered Arctic seas to the warm tropical oceans, from shallow coastal waters to the deepest ocean trenches, whales had evolved to exploit every available ecological niche in the marine realm. The diversity of modern whale species reflects this long history of evolutionary experimentation and adaptation. Each species represents a different solution to the challenges of marine life, whether it's the massive blue whale filtering tiny krill from Antarctic waters, the deep-diving sperm whale hunting giant squid in oceanic trenches, or the highly social orca using cooperative strategies to hunt a wide variety of prey in coastal environments. The intelligence and social complexity that characterizes modern whales emerged gradually over millions of years of evolution, driven by the challenges and opportunities of life in complex marine environments. The ability to learn from experience, to communicate sophisticated information to other individuals, and to develop cultural traditions that enhance survival became as important as physical adaptations in determining evolutionary success. The conservation challenges facing modern whales remind us that even the most successful evolutionary stories can be vulnerable to rapid environmental changes. The whales that survived ice ages, sea level changes, and massive volcanic eruptions now face new challenges from human activities that are altering ocean environments at unprecedented rates. Understanding the remarkable evolutionary history of whales provides crucial insights into their resilience and adaptability, while also highlighting their vulnerability to rapid environmental changes. These magnificent animals represent one of evolution's greatest success stories, demonstrating the power of natural selection to transform organisms in response to new opportunities and challenges. The story of whale evolution continues in our modern oceans, where these remarkable animals face new selective pressures that will shape their future evolution. As climate change alters ocean temperatures and circulation patterns, as human activities modify marine ecosystems, and as new technologies allow us to study whale behavior and biology in unprecedented detail, we are witnessing the ongoing chapter of one of evolution's most extraordinary transformations. The whales that grace our contemporary oceans carry within their genes and behaviors the accumulated wisdom of 50 million years of evolutionary experience. They are living libraries of adaptation, intelligence, and resilience, representing alternative solutions to the challenges of complex life that took a path through the ocean rather than remaining on land. Their presence in our world serves as a reminder of the remarkable creativity of evolutionary processes and the incredible diversity of forms that life can take when given sufficient time and opportunity. The story of their return to the sea speaks to the fundamental adaptability of life and the surprising directions that evolution can take when environmental conditions create new possibilities for survival and reproduction. As these magnificent creatures continue their ancient migrations through ocean basins that bear the marks of their evolutionary history, they carry forward a legacy that spans geological ages. Each breath they take at the ocean's surface, each dive into the depths, each song that echoes through the underwater world, represents the continuation of one of the most remarkable evolutionary journeys in the history of life on Earth. In the gentle rhythm of their breathing and the graceful power of their movement through the water, we can still perceive echoes of that ancient transformation that began 50 million years ago when their terrestrial ancestors first ventured into the shallows of primordial seas. They remind us that evolution is not merely a process of the past, but a continuing force that shapes life in ways that continue to surprise and inspire us. The whales of today are both ancient and modern, carrying forward evolutionary innovations that have been tested and refined over countless generations while continuing to adapt to the challenges of an ever-changing world. They represent the triumph of life's ability to reinvent itself, to explore new possibilities, and to create forms of beauty and complexity that exceed our capacity to fully comprehend. Their story of return to the sea stands as one of the most compelling examples of evolution's power to transform life in fundamental ways while preserving the essential characteristics that make complex organisms successful. In their intelligence, their social bonds, and their remarkable adaptations for marine life, we see reflected both the deep history of mammalian evolution and the endless possibilities that await life in the vast expanses of our planet's oceans. The transformation we've witnessed over these millions of years represents far more than simple anatomical change. It reveals something profound about the nature of life itself, about how organisms respond to opportunity with creativity that seems almost intentional, yet unfolds through the patient work of natural selection across countless generations. By the end of the Miocene epoch, roughly 5 million years ago, the oceans had become home to creatures that would have been unrecognizable to observers from that ancient Eocene world where our story began. The warm, shallow seas that had nurtured Pachycetus and Ambulocetus had given way to cooler, deeper waters with complex current systems that carried nutrients across vast distances, creating the rich feeding grounds that would support the next chapter in whale evolution. The climate during this period continued its gradual cooling trend, with ice beginning to accumulate at both poles for the first time in millions of years. This cooling had profound effects on ocean circulation, creating the first hints of the powerful upwelling systems that would eventually support the massive whale populations we see today. Cold, nutrient-rich water from the depths began to rise to the surface in predictable patterns, bringing with it the minerals that would fuel explosive blooms of marine life. In these changing seas, the descendants of those early whales faced new challenges and discovered new possibilities. The relatively uniform ocean environments of earlier epochs were giving way to a more complex mosaic of marine habitats, each offering different opportunities for specialized feeding strategies. Some whale lineages began to focus their evolutionary efforts on exploiting these emerging ecological niches, while others maintained the flexibility to adapt to changing conditions as they arose. The fossil record from this crucial period shows us whales that were becoming increasingly sophisticated in their approach to marine life. Their brains had grown larger and more complex, with expanded areas dedicated to processing acoustic information and coordinating the intricate behaviors necessary for success in three-dimensional underwater environments. The social bonds between individuals strengthened, creating family groups that could share information about feeding areas and migration routes across generations. During the Pliocene epoch, roughly 5 to 2 million years ago, we begin to see the emergence of the first truly massive whales. These were not quite the giants we know today, but they represented a significant step toward the gigantism that would characterize many modern species. The key to understanding this growth lies in recognizing how the changing ocean environment was creating new opportunities for large-scale filter feeding. As global temperatures continued to drop and seasonal patterns became more pronounced, the oceans began to experience dramatic seasonal blooms of plankton and krill. These tiny organisms, which had always been present in marine ecosystems, suddenly began appearing in concentrations that had never existed before. Vast swarms of krill, sometimes extending for dozens of miles across the ocean's surface, created feeding opportunities that could support much larger whales than had ever been possible. The evolutionary response to this abundance was remarkable. Baleen whales began to grow larger, generation by generation, as natural selection favored individuals who could process greater volumes of these rich feeding grounds. Their mouths expanded to accommodate more baleen plates, their throat pleats became more numerous and more expandable, and their overall body size increased to support the massive feeding apparatus required for efficient filter feeding. This period also saw the refinement of what scientists call lunge feeding, a revolutionary technique that allowed whales to capture enormous quantities of prey in a single feeding event. Rather than swimming slowly through the water with their mouths open, these advanced filter feeders learned to accelerate rapidly toward concentrations of krill, opening their massive mouths to engulf huge volumes of water and prey in one tremendous gulp. The mechanics of lunge feeding required extensive modifications to whale anatomy. The lower jaw evolved special joints that allowed it to dislocate slightly during feeding, while the throat pleats developed the ability to expand the mouth cavity by several times its resting volume. The tongue became a massive muscular structure capable of forcing hundreds of tons of water out through the baleen plates, while retaining the krill suspended within. Meanwhile, the toothed whales were pursuing their own evolutionary innovations. The echolocation abilities that had begun to develop millions of years earlier were reaching new levels of sophistication. Some species could now echolocate objects as small as a coin buried in sand, while others developed the ability to peer deep into the bodies of other animals, essentially seeing through flesh to examine internal structures. The social implications of these advancing abilities were profound. Toothed whales began to develop complex cooperative hunting strategies that required precise coordination between multiple individuals. Groups of dolphins learned to work together to create mud nets that trapped schools of fish, while others developed techniques for herding prey into shallow water where escape was impossible. The communication systems of whales during this period became increasingly elaborate. The songs of humpback whales, which can last for hours and travel across entire ocean basins, evolved as these animals grew larger and more capable of producing powerful acoustic signals. These songs serve multiple functions, from attracting mates across vast distances to coordinating feeding activities and maintaining social bonds within widely dispersed populations. The development of whale migration patterns during the Pliocene represents one of nature's most impressive logistical achievements. As seasonal differences in food availability became more pronounced, whales evolved the ability to undertake journeys of thousands of miles to follow their prey or reach suitable breeding areas. These migrations required not only tremendous physical endurance, but also sophisticated navigation abilities that allowed whales to find their way across seemingly featureless ocean expanses. The precision of whale navigation continues to amaze scientists today. Modern whales can return to the same feeding areas year after year with remarkable accuracy, suggesting that they possess multiple navigation systems that work together to provide redundant positioning information. Magnetic sensing appears to provide a reliable compass system, while the position of celestial bodies offers additional navigational references for animals that spend significant time at the ocean's surface. Underwater sound channels created by differences in water temperature and salinity allow whales to use acoustic landmarks that can be detected from hundreds of miles away. The songs of other whales, the sounds of breaking waves on distant shores, and even the acoustic signatures of underwater geological features all contribute to a rich acoustic landscape that whales can use for navigation and orientation. The physiological demands of long-distance migration drove continued evolution in whale anatomy and metabolism. The heart grew larger and more efficient, capable of maintaining circulation during months of nearly continuous swimming. The muscles developed enhanced capacity for storing oxygen and metabolizing fat, allowing whales to undertake journeys lasting several months while feeding minimally or not at all. The blubber layer became increasingly sophisticated during this period, serving functions far beyond simple insulation. Different regions of the blubber evolved specialized properties, with some areas optimized for energy storage, others for hydrodynamic efficiency, and still others for thermal regulation. The distribution and thickness of blubber became highly species-specific, reflecting the different thermal challenges faced by whales in various ocean environments. As we move into the Pleistocene epoch, roughly 2 million to 10,000 years ago, we encounter the final stages of whale evolution that would produce the magnificent creatures we know today. This period was characterized by dramatic climate fluctuations, with ice ages alternating with warmer interglacial periods every 100,000 years or so. These climate cycles had profound effects on ocean environments and whale populations. During ice ages, sea levels dropped by several hundred feet, as vast quantities of water were locked up in continental ice sheets. This exposed large areas of the continental shelf, dramatically altering coastal marine habitats and forcing whales to adapt to changing ocean geography. The formation of massive ice sheets also altered ocean circulation patterns, creating new upwelling zones and changing the distribution of marine productivity. The whales that survived these dramatic environmental changes were those with the greatest flexibility in their feeding strategies and migration patterns. Some species learned to exploit the rich feeding opportunities created by melting ice edges, while others developed the ability to fast for extended periods during unfavorable conditions. The largest whales, with their massive energy reserves stored in blubber, were particularly well suited to surviving these boom and bust cycles. It was during the later Pleistocene that baleen whales finally achieved the enormous sizes that characterize many modern species. The blue whale, which can reach lengths of over 100 feet and weights exceeding 200 tons, represents the culmination of millions of years of evolutionary refinement. These giants are not merely scaled-up versions of smaller whales, but represent fundamentally different approaches to marine life that are only possible at such enormous scales. The gigantism of modern baleen whales is intimately connected to the productivity patterns of contemporary oceans. The seasonal blooms of krill and other small organisms that characterize polar and subpolar waters can support filter-feeding whales of unprecedented size, but only because these feeding opportunities are so rich and concentrated. A blue whale feeding in Antarctic waters during the summer can consume up to 4 tons of krill per day, storing enough energy to sustain itself during the long journey to warmer breeding waters. The reproductive strategies of giant whales reflect the unique challenges of their enormous size. Gestation periods became extended to allow whale calves to reach a more advanced stage of development before birth, while the milk produced by whale mothers became incredibly rich in fat to support rapid growth of young whales. A blue whale calf can gain over 200 pounds per day during its first year of life, fueled by milk that is nearly 40% fat. The social structures of whale communities also evolved to accommodate the challenges of their enormous size and oceanic lifestyle. Family groups became more dispersed across vast areas, with individuals maintaining contact through long-distance vocalizations rather than close physical proximity. The bonds between mothers and calves intensified as young whales required extended periods of parental care to learn the complex behaviors necessary for survival in the open ocean. The cultural transmission of knowledge became increasingly important in whale societies as their ranges expanded and their behaviors became more complex. Information about feeding areas, migration routes, and seasonal patterns had to be passed from generation to generation to ensure the survival of whale populations. This cultural knowledge became as important as genetic adaptations in determining the success of different whale lineages. The acoustic world of giant whales expanded to match their physical scale. The low-frequency calls of blue whales can travel for hundreds of miles underwater, allowing these massive animals to maintain contact across distances that would have been impossible for smaller species. These infrasonic communications, operating below the range of human hearing, create an acoustic network that spans entire ocean basins, The diving abilities of whales also reached extraordinary levels during this final phase of their evolution. Sperm whales developed the ability to dive to depths exceeding 6,000 feet, remaining submerged for over an hour while hunting giant squid in the permanent darkness of the deep ocean. These extreme diving capabilities required sophisticated adaptations in blood chemistry, lung structure, and pressure tolerance that pushed the limits of what is physiologically possible for air-breathing mammals. The success of whales in exploiting virtually every available niche in the marine environment represents one of evolution's most complete adaptive radiations. From the massive blue whales filtering krill in polar waters to the highly intelligent orcas using complex cooperative strategies to hunt marine mammals. From the deep-diving sperm whales pursuing squid in oceanic trenches to the agile dolphins coordinating their movements with sophisticated echolocation. The diversity of modern cetaceans reflects millions of years of evolutionary experimentation and refinement. The intelligence that characterizes modern whales emerged gradually over this long evolutionary history, driven by the complex challenges of three-dimensional navigation, sophisticated social coordination, and the need to locate and exploit patchily distributed resources across vast ocean spaces. The large brains of whales, with their highly developed cerebral cortex and complex neural architecture, enable cognitive abilities that rival those of the most intelligent terrestrial mammals. The conservation challenges facing modern whales remind us that even the most successful evolutionary stories remain vulnerable to rapid environmental change. The whales that survived ice ages, volcanic eruptions, and massive shifts in ocean chemistry now face new pressures from human activities that are altering marine environments faster than evolutionary processes can respond. Understanding their remarkable evolutionary history provides crucial context for appreciating both their resilience and their vulnerability in our rapidly changing world. The story of whale evolution offers profound insights into the nature of life itself and the remarkable creativity of natural selection. Over the course of 50 million years, these animals transformed from small, wolf-like terrestrial mammals into the largest creatures ever to exist on Earth, while retaining the intelligence, social complexity, and behavioral flexibility that characterize advanced mammals. Their success demonstrates that evolution is not simply a process of gradual change, but can produce revolutionary transformations when the right opportunities arise. The fossil record of whale evolution stands as one of the most complete and well-documented examples of major evolutionary transition available to science. From Pakicetus, hunting fish in ancient rivers, to blue whales filtering krill in modern oceans, this transformation provides a detailed window into how life responds to new environments and opportunities. Each fossil discovery adds new chapters to this remarkable story, revealing unexpected details about the pathways that led to modern whale diversity. The techniques that paleontologists use to study whale evolution continue to reveal new insights about these ancient transformations. Advanced imaging technologies allow scientists to examine internal structures of fossil skulls, revealing details about brain evolution and sensory capabilities that would have been impossible to detect just a few decades ago. Chemical analysis of fossil teeth provides information about ancient diets and habitats, while biomechanical studies help us understand how extinct whales moved and fed. The molecular evidence for whale evolution, derived from DNA analysis of modern species, provides independent confirmation of the relationships revealed by fossil studies. The genetic signatures preserved in whale DNA tell the same story as the bones buried in ancient rocks, confirming that whales are most closely related to hippos among living mammals, and that all modern cetaceans descended from a common ancestor that lived approximately 50 million years ago. The study of whale evolution has also contributed to our understanding of broader evolutionary principles. The rapid transformation of these animals from terrestrial to fully aquatic lifestyles demonstrates how quickly major evolutionary changes can occur when strong selective pressures favor new adaptations. The parallel evolution of similar features in different whale lineages shows how natural selection tends to produce similar solutions to similar environmental challenges. The ongoing evolution of whales in our modern oceans reminds us that evolutionary change is not a process confined to the distant past. As climate change alters ocean temperatures and circulation patterns, as human activities modify marine ecosystems, and as new diseases and parasites emerge, whale populations continue to face selective pressures that will shape their future evolution. Some populations are already showing genetic and behavioral adaptations to changing environmental conditions. The remarkable journey of whales from land to sea serves as a powerful reminder of life's extraordinary capacity for transformation and adaptation. These magnificent animals represent one of evolution's greatest success stories, demonstrating that even the most fundamental aspects of an organism's lifestyle can be completely reinvented when environmental opportunities arise. Their story speaks to the endless creativity of natural selection and the surprising directions that evolution can take when given sufficient time and opportunity. In the gentle rise and fall of a whale's breathing at the ocean's surface, in the graceful power of its movement through the water, in the haunting beauty of its songs that echo through the depths, we can still perceive the echoes of that ancient transformation that began 50 million years ago. These animals carry within their bodies and behaviors the accumulated wisdom of countless generations of evolutionary refinement, representing a living bridge between the terrestrial past and the oceanic present. The whales that grace our modern seas are both ancient and contemporary, carrying forward adaptations that have been tested and perfected over millions of years, while continuing to respond to the challenges of an ever-changing world. They remind us that evolution is not merely a historical process, but a continuing force that shapes life in ways that continue to surprise and inspire us. Their presence in our oceans serves as a testament to the resilience and adaptability of life, to the power of gradual change to produce extraordinary results, and to the deep connections that link all living things across the vast expanses of evolutionary time. In their intelligence, their grace, and their remarkable adaptations for marine life, we see reflected both the ancient history of mammalian evolution and the endless possibilities that await life in the vast blue spaces of our planet's oceans. As these gentle giants continue their eternal migrations through waters that have witnessed 50 million years of evolutionary change, they carry with them a message of hope and wonder. They remind us that life finds a way not merely to survive, but to flourish, creating forms of beauty and complexity that exceed our wildest imagination. In their story of return to the sea, we find inspiration for our own journey through time, a reminder that transformation and renewal are always possible when we remain open to the vast possibilities that surround us. The ocean depths, where whales now make their home, echo with the songs of creatures that have traveled an evolutionary path unlike any other in the history of life on Earth. Their voices, carrying across vast underwater distances, speak of ancient transformations and continuing adaptations, of the patient work of natural selection across countless generations, and of the enduring power of life to reinvent itself in the face of changing worlds. The gentle currents of our modern oceans carry within them the echoes of this extraordinary transformation, a story written not in words but in the very bones and DNA of creatures that have mastered two worlds. As we drift through these final chapters of whale evolution, we find ourselves witnessing the emergence of animals so perfectly adapted to their marine realm that they seem to have been designed by the ocean itself. During the closing millennia of the Pleistocene, roughly 12,000 years ago, the last great ice age was drawing to an end. Massive ice sheets that had locked away tremendous volumes of seawater began their final retreat, causing ocean levels to rise and flooding vast areas of the continental shelf. This dramatic transformation of marine geography created new habitats and feeding opportunities that would shape the final refinements of whale evolution. The warming oceans of this period supported explosive blooms of marine life. microscopic phytoplankton multiplied in unprecedented numbers as melting ice released nutrients that had been frozen for millennia. These tiny organisms formed the foundation of food webs that could support whale populations larger and more diverse than had ever existed before. The stage was set for the final flowering of whale gigantism and specialization. In the nutrient-rich waters of the newly ice-free Arctic, the ancestors of modern bowhead whales were developing their remarkable adaptations for life in polar seas. Their skulls grew massive and reinforced, capable of breaking through ice several feet thick to create breathing holes in the frozen surface. Their baleen became the longest and most flexible of any whale species, allowing them to filter the tiny copepods and other organisms that thrived in the brief but incredibly productive Arctic summer. The bowhead's mouth became a cavernous chamber, with baleen plates extending up to 14 feet in length, creating a filtering system of unparalleled efficiency. Their bodies grew thick and robust, insulated by blubber that could exceed 2 feet in thickness, providing protection against water temperatures that hovered just above freezing throughout much of the year. These adaptations allowed bowhead whales to thrive in one of Earth's most challenging environments, following the seasonal retreat and advance of polar ice with remarkable precision. Meanwhile, in the warmer waters of temperate and tropical seas, other whale lineages were pursuing different evolutionary strategies. The ancestors of modern grey whales developed a unique feeding technique that set them apart from all other baleen whales. Rather than filtering organisms from the water column, these innovative feeders learned to dive to the shallow ocean floor and scoop massive mouthfuls of sediment, straining out the tiny crustaceans and worms that lived in the mud. This bottom-feeding strategy required specialized adaptations that distinguished grey whales from their relatives. Their baleen became shorter and more robust, better suited for filtering prey from muddy water rather than clear seawater. Their heads developed a distinctive shape, with a narrow upper jaw that could be pushed deep into soft seafloor sediments. Most remarkably, they evolved the ability to feed primarily on one side of their body, creating an asymmetry that reflected their specialized feeding technique. The grey whale's migration pattern became one of the most extensive undertakings in the animal kingdom. These remarkable creatures learned to travel over 12,000 miles annually, journeying from rich feeding grounds in the Arctic to warm water breeding lagoons along the coasts of Mexico and California. This epic journey required navigating through diverse ocean environments, from the ice-filled waters of the Bering Sea to the warm, shallow lagoons where they gave birth to their calves. The physiological demands of such extreme migrations drove further refinements in whale anatomy and metabolism. Grey whales developed the ability to fast for up to 8 months during their reproductive cycle, living blubber reserves while entirely off energy stored in their massive travelling and breeding. Their digestive systems became dormant during these extended fasting periods, then rapidly reactivated when they returned to their Arctic feeding grounds. In the deep waters far from shore, the ancestors of modern sperm whales were perfecting their mastery of the ocean's most challenging frontier. The abyssal depths, with their crushing pressures and eternal darkness, had remained largely unexplored by marine mammals until these remarkable creatures evolved the physiological adaptations necessary to hunt in environments that seemed almost alien in their extremity. The sperm whale's distinctive rectangular head, which comprises nearly 1/3 of its total body length, houses the largest brain of any animal that has ever lived. But this massive cranium serves functions far beyond simple intelligence. Within its depths lies the spermaceti organ, a complex structure filled with waxy oils that plays crucial roles in both echolocation and diving physiology. This organ can be adjusted to change the whale's buoyancy, allowing precise control during deep dives that can exceed depths of 7,000 feet. The echolocation abilities of sperm whales represent the pinnacle of biological sonar development. These animals can produce the loudest sounds in the animal kingdom, acoustic pulses so powerful they can stun or even kill their prey. The clicks generated by sperm whales can travel for miles through the deep ocean, allowing them to locate and track the giant squid that form their primary food source in the perpetual darkness of the abyss. The hunting behavior of sperm whales in the deep ocean reads like science fiction brought to life. In the complete darkness of depths, where no sunlight has ever penetrated, these massive predators engage in battles with giant squid that can exceed 40 feet in length. The circular scars left by squid tentacles on whale skin tell stories of encounters that occur in an alien world as remote from human experience as the surface of another planet. The social structure of sperm whale communities reflects their unique lifestyle and extreme diving abilities. Female sperm whales and their young live in closely bonded family groups that remain at the surface, while individual adults take turns diving to incredible depths to hunt. These matrilineal societies maintain complex social relationships through sophisticated vocalizations, with different families possessing distinct vocal dialects that serve as acoustic signatures, identifying their lineage. The cultural transmission of hunting knowledge becomes particularly important for sperm whales, as the skills required for deep-sea hunting cannot be learned through instinct alone. Young whales must learn not only the physical techniques of deep diving, but also the complex acoustic skills necessary for echolocating prey in the abyss. This cultural learning process can take many years, with adolescent whales gradually developing the abilities that will allow them to become independent deep-sea hunters. The respiratory adaptations of deep-diving whales represent some of the most extreme physiological modifications found in any mammal. Before beginning a deep dive, sperm whales exhale most of the air from their lungs, preventing nitrogen narcosis and reducing buoyancy. Their blood contains extraordinarily high concentrations of oxygen-carrying proteins, while their muscles store additional oxygen in specialized proteins that release it gradually during extended dives. The cardiovascular system of diving whales undergoes dramatic changes during deep submersion. Heart rate slows dramatically, while blood flow is redirected away from non-essential organs toward the brain and other vital structures. The whale's metabolism shifts into a low-energy mode that allows it to function on minimal oxygen supplies for extended periods. These adaptations allow sperm whales to remain submerged for over an hour while hunting in the deepest parts of the ocean. As we move into the modern era, the final 10,000 years of whale evolution, we encounter creatures that had achieved a level of adaptation to marine life that seems almost perfect in its completeness. The whales of the Holocene epoch, our current geological period, represent the culmination of 50 million years of evolutionary refinement. Animals so thoroughly aquatic that they seem to belong more to the ocean than to the terrestrial realm from which their ancestors emerged. The diversity of modern whale species reflects the full exploitation of available marine ecological niches. In the frigid waters of Antarctica, blue whales had achieved sizes that pushed the absolute limits of what is physically possible for a living organism. These gentle giants, measuring over 100 feet in length and weighing up to 200 tons, represent not just the largest whales, but the largest animals that have ever existed on Earth. The feeding strategy of blue whales during the Antarctic summer demonstrates the incredible efficiency of their evolutionary design. A single blue whale can consume up to 4 tons of krill per day, processing over 16,000 gallons of seawater during each feeding lunge. Their enormous mouths, when fully extended during feeding, can hold volumes of water equivalent to their own body weight. The coordination required to manage such massive feeding operations while swimming at high speeds represents a masterpiece of evolutionary engineering. The reproductive cycle of blue whales reflects the extreme demands of their gigantic size and oceanic lifestyle. Gestation lasts nearly a year, producing calves that are already 24 feet long and weigh nearly 3 tons at birth. The milk produced by blue whale mothers contains over 30% fat, enabling calves to gain up to 200 pounds per day during their first year of life. These growth rates, necessary to quickly develop the size and blubber reserves needed for survival in cold ocean water, are among the fastest recorded in the animal kingdom. The vocalizations of blue whales create an acoustic landscape that spans entire ocean basins. Their calls, operating at frequencies below the range of human hearing, can travel for hundreds of miles underwater under favorable conditions. These infrasonic communications allow blue whales to maintain contact with potential mates and family members across distances that would otherwise make social coordination impossible for such far-ranging animals. The migration patterns of blue whales represent some of the longest journeys undertaken by any animal. Individual whales have been tracked traveling over 5,000 miles between feeding and breeding areas, following ocean currents and temperature gradients with remarkable precision. These epic journeys require not only tremendous physical endurance, but also navigation abilities that incorporate multiple sensory systems working in perfect coordination. In the warmer waters of tropical and temperate seas, other whale lineages had evolved their own remarkable specializations. The humpback whale, with its extraordinarily long pectoral fins and complex behavioral repertoire, represents perhaps the most behaviorally sophisticated of all baleen whales. Their feeding techniques include cooperative bubble netting, where groups of whales work together to create walls of bubbles that concentrate schools of small fish, making them easier to capture. The songs of humpback whales have become among the most studied acoustic displays in the animal kingdom. These complex vocalizations, which can last for hours and evolve over time within populations, serve multiple functions from long-distance communication to courtship displays. Each population of humpback whales maintains its own distinct song tradition, with new phrases and themes being added while others are abandoned, creating a form of cultural evolution that parallels genetic change. The acrobatic abilities of humpback whales, including their spectacular breaching behavior, demonstrate the remarkable power and agility that these massive animals have achieved despite their enormous size. A 40-ton humpback whale can launch itself completely out of the water, a feat that requires generating tremendous thrust with its powerful tail fluke. The purpose of such energetically expensive behaviors remains partially mysterious, though they likely serve functions related to communication, parasite removal, and social interaction. The coastal waters of the world's oceans became home to some of the most intelligent and socially complex whale species. Orcas, the largest members of the dolphin family, evolved into highly specialized predators capable of hunting everything from fish and squid to other marine mammals, including whales much larger than themselves. Their success stems not just from their physical capabilities, but from their extraordinary intelligence and sophisticated social organization. Orca societies are built around matrilineal family groups led by elderly females whose knowledge and experience guide the hunting and social activities of their descendants. These family groups, or pods, maintain distinct vocal dialects that serve as acoustic signatures identifying their lineage. The cultural knowledge passed down through these family lines includes detailed information about hunting techniques, seasonal movements of prey, and navigational landmarks that may be crucial for survival in challenging ocean environments. The hunting strategies of different orca populations demonstrate the remarkable flexibility of their evolved intelligence. Some populations specialize in hunting salmon and other fish, using sophisticated echolocation to locate schools of prey and coordinating their movements to maximize capture success. Others have become specialists in hunting marine mammals, employing techniques that require extraordinary cooperation and planning, such as deliberately beaching themselves to capture seals resting on shore. The tool use behaviors observed in some orca populations represent some of the most sophisticated examples of this capability outside of primates. Some groups have learned to use sea sponges as protective masks while foraging along rough seafloors, while others employ kelp fronds and other objects in their hunting activities. These behaviors are culturally transmitted from mother to offspring, creating local traditions that can persist for generations. The sensory world of modern toothed whales represents the pinnacle of acoustic evolution. Dolphins and porpoises can echolocate objects with precision that exceeds the best human sonar technology, distinguishing between items that differ by mere millimeters in size or detecting objects buried several feet beneath sandy seafloors. Their acoustic processing abilities allow them to create detailed three-dimensional maps of their underwater environment, using nothing but sound waves and their biological interpretation systems. The social complexity of dolphin societies rivals that of the most advanced terrestrial mammals. These highly intelligent animals form intricate alliance networks that can span multiple generations, with individuals cooperating in hunting, defense, and reproduction activities. The communication systems of dolphins include not only echolocation calls, but also signature whistles that function as individual names, allowing specific identification of community members across considerable distances. The problem-solving abilities and self-awareness demonstrated by whales and dolphins in experimental settings reveal cognitive capabilities that were entirely unexpected when first discovered. These animals can recognize themselves in mirrors, use abstract symbols to communicate with humans, and demonstrate understanding of complex concepts including numerical relationships and grammatical structures in artificial languages. The physiological adaptations that allow whales to thrive in marine environments continue to inspire human technological development. The hydrodynamic efficiency of whale skin has influenced the design of ship hulls and underwater vehicles, while their echolocation systems have provided insights for improving sonar and medical imaging technologies. The ability of whales to dive to extreme depths while avoiding decompression sickness has contributed to advances in diving medicine and underwater exploration techniques. And so we reach the end of our journey through deep time, a story that began with small wolf-like creatures padding along the muddy shores of ancient seas and concludes with the magnificent whales that grace our modern oceans. From Pachycetus, taking its first tentative steps into shallow water 50 million years ago to the blue whales that now traverse entire ocean basins, we have witnessed one of evolution's most extraordinary transformations. The whales swimming in today's seas carry within their bodies the memory of land, the echo of legs that once walked, and the legacy of ancestors who dared to venture into an alien world of water. Their blowholes speak of nostrils that once sniffed terrestrial air, their flippers remember fingers that once grasped solid ground, and their songs carry melodies that began as simple calls across primordial rivers. In the gentle rise and fall of a whale's breathing at the surface, in the graceful arc of its dive toward the depths, we see the culmination of millions of years of patient change. Each generation building upon the adaptations of those who came before, each small modification adding to a transformation so complete that these ocean giants seem as natural in water as if they had never known any other home. The story of whales reminds us that life is endlessly creative, always ready to explore new possibilities when opportunity presents itself. It tells us that even the most fundamental aspects of existence can be reimagined, that bodies shaped by millions of years of terrestrial life can be completely redesigned for an aquatic world. Most of all, it whispers to us that in the vast expanses of time, anything becomes possible. As you drift towards sleep tonight, perhaps you can hear the distant songs of whales echoing through dark waters, carrying messages across ocean basins, connecting past to present in an unbroken chain of evolutionary wonder. They remind us that we are all part of this same magnificent story of life on Earth, forever changing, forever adapting, forever finding new ways to flourish in an ever-changing world.